An important but often overlooked aspect of the development of a scientific treatment of a physical domain consists in the accumulation of data. This accumulation of data serves a number of really important purposes. You need to have a sufficiently broad and accurate understanding of the actual behavior of the elements of a domain in order to categorize and develop theoretic models of those elements of the domain. Data accumulation can serve to refine ontological frameworks and categories. It begins with initial inquiry, but it continues throughout the development of a science, even into maturity and normal science. One example of data accumulation from our chapter that nicely illustrates its importance over time was isochronism. Recall that isochronism was the claim made by Galileo that no matter how far you displace the pendulum bob from its center equilibrium point, that is, no matter how big the pendulum swim becomes, the periodicity will remain the same because gravity will accelerate that bob all the more the farther you pull it back. When Christian Huygens and others started to investigate pendulum motion, particularly with an eye towards employing pendulums in pendulum clocks, what they discovered was that isochronism starts to fail between 4 and 6 degrees. This graph here illustrates that relationship. As you increase the angle from which you displace the pendulum bob, you in fact actually change the periodicity of the pendulum swing. A similar example can be seen in Galileo's uniform gravitational acceleration. And we really shouldn't just attribute it to Galileo. This is a pretty common conception even today. The idea behind uniform gravitational acceleration is that objects will accelerate at the same rate in the Earth's gravitational field no matter what their mass is. This is, in general, a pretty good rule of thumb, but it's technically false. And in fact, though it took some 400 years, in 2002, NASA launched the Gravity Recovery and Climate Experiment, or GRACE, satellite. The mission produced maps of the variation of the Earth's mass, and hence gravity, indicating that acceleration due to gravity varies depending upon latitude, altitude, and depth. Indeed, the net component of the Earth's gravity available to accelerate objects decreases as one approaches the equator because of the Earth's rotation. Equatorial objects lie at a greater distance from the Earth's center. As a result, they rotate faster. Faster rotational motion results in greater centrifugal force, meaning that a greater share of gravitational attraction is required to redirect an object's trajectory to keep it in place in rotation around the Earth, as opposed to the object, say, continuing in a straight trajectory. Centrifugal force increases with the distance from the Earth, as well as with increases in angular velocity, ultimately completely nullifying gravitational attraction and resulting in the weightlessness experienced by astronauts. Gravitational acceleration ranges from a value of 9.78 meters per second squared at the equator to a value of 8.32 meters per second squared at the Earth's poles. Additionally, features like mountains increase localized mass, increasing localized gravitational attraction. Gravity and its effects aren't the only examples, though, of data accumulation. Until the early 90s, it was considered to be established fact that the brain does not generate new cells. There is no neurogenesis. But as we'll see, it was discovered that in fact certain areas in the brain, for instance the hippocampus, do in fact have neurogenesis. In its most conservative formulation, an experimental tradition consists of a set of accepted experimental designs and apparatus. I take a larger view of experimental traditions in order to accommodate their emergence and evolution over time. Before theorists can formulate dynamical or attributional models for a domain, they need to be able to tie the categories of an ontological framework to the phenomenon of the candidate domain more closely. Simple operationalizations, like observation by the naked eye or simple measurements, initially help to tie the categorizations of an ontological framework more tightly to the phenomenon. But as theorists begin to formulate theoretic models, they require increasingly subtle and precise methods for operationalizing categories and testing theoretic models. Researchers begin to develop or adapt experimental methodologies and apparatus to test their models, often by fixing or controlling certain aspects of the phenomenon in order to isolate and observe others. To better understand the significance of the data that they collect, theorists also need to develop tools and conventions for helping them to determine the import of their data for their models. Thus, in the context of this text and course, we can think of an experimental tradition as incorporating operationalizations, experimental designs, instruments and apparatus, as well as tools and techniques for data analysis. Since we discussed operationalizations earlier, this part of the lecture will focus on experimental designs, instruments, and apparatus, as well as tools and techniques for data analysis. There are several examples of experimental designs in the chapter that illustrate this more expansive notion of an experimental tradition and show how various elements are integrated together in a single experimental design. For example, when we talked about Galileo's use of inclined planes to measure the value for g, what we saw was that Galileo introduces an apparatus, the inclined plane, in order to slow the acceleration due to gravity for balls so that he can measure it using his less accurate instrument of a water clock. In doing so, he creates an experimental design that facilitates a much more sophisticated operationalization of the value for g and hence tightens the connection between that category and the phenomenon in the real world. His measurement is pretty accurate given his instruments. Our normal measurement for gravitational acceleration is 9.81 meters per second squared. Galileo's value was 10.8 meters per second squared. Another example of an experimental design that integrates elements of our more expansive notion of an experimental tradition is null hypothesis testing. In null hypothesis testing, scientists work to isolate a single feature of some phenomenon by creating a control group and an experimental manipulation group that differ only in that feature. They then use statistical techniques for data analysis to determine the significance of highly variable data that they get from those experiments. Overall, we see a number of examples and illustrations of the various components that we mentioned in this more expansive notion of an experimental tradition. For instance, with operationalizations, we've seen counting, measuring, taxonomies. With experimental designs, we've seen things like the null hypothesis design. We'll look at the habituation paradigm later on. We've seen a number of different apparatus, the tachyoscope that was introduced, the telescope, and the water clock, just to name a few. We've also seen a number of tools that get developed, and we'll expand on this when we look at psychology, for analyzing data from experiments when that data is highly variable to help theorists and researchers understand the significance of the data that they collect through their experiments. In the next lecture module, we'll turn our attention to the notion of a theoretic model, and I'll talk about both dynamical and attributional models,